Welcome to the world of entropy, a powerful idea that connects physics, information theory, and machine learning. At first glance, entropy might seem abstract, but it actually explains many things around us, from the way heat spreads to how we compress data, and even how machines learn. Let's begin our journey by understanding entropy in the most classical sense, through thermodynamics. In thermodynamics, entropy is defined as a measure of disorder or randomness within a system. The more chaotic the system, the higher the entropy. It is denoted by the symbol S and plays a key role in the second law of thermodynamics, which states that the entropy of an isolated system never decreases over time. This is expressed mathematically as delta S equals Q sub rev divided by T, where ds is the change in entropy. Q sub rev represents the reversible heat transfer, and T is the absolute temperature in Kelvin. Imagine ice melting into water, or gas particles dispersing in a container. Both are examples of increasing entropy. Now that we've seen how entropy operates in the physical world, let's explore how it applies to information itself. Moving into the realm of information theory, entropy takes on a new meaning: uncertainty. Introduced by Claude Shannon, entropy here measures how unpredictable a message or data source is. The formula reads, h of x equals negative, the sum over I of p of x sub I times log base 2 of p of x sub I. For example, a fair coin flip has two equally likely outcomes, giving us maximum entropy of 1 bit. That's written as h of x equals negative open bracket 0.5 log base 2 of 0.5 plus 0.5 log base 2 of 0.5 close bracket equals 1 bit. In contrast, a biased coin with a 90% chance of landing heads and 10% tails has lower entropy, approximately 0.469 bits. Because it's more predictable, there's less uncertainty, and therefore lower entropy. This idea of measuring uncertainty becomes especially useful when applied to machine learning. In machine learning, entropy is used to evaluate uncertainty and guide decision-making in models. One key application is in cross-entropy loss, which compares how far off a predicted probability distribution is from the actual distribution. The formula sounds like this: h of p and q equals negative the sum over I of p of x sub I times log of q of x sub I. This is essential for classification tasks, helping the model learn to predict better over time. Entropy also shows up in decision trees, where it helps determine how to split data. Here, entropy measures the impurity of a node, and the information gain formula reads, gain equals h of parent minus the sum of n sub I over n times h of child sub I. By selecting the feature that results in the largest reduction in entropy, the tree grows in a more optimal and informative way. But even beyond algorithms, entropy carries meaning that we can relate to on a human level. To make it more intuitive, think of entropy as the amount of surprise you experience when an event occurs. If something is very likely, like getting your daily notification or rewatching a movie, there's little to no surprise, and thus low entropy. But when something unexpected happens, like a surprise plot twist or a rare outcome, you feel that wow moment. That's high entropy. So the more unpredictable the result, the higher the entropy. This intuitive grasp helps bridge our understanding between math and real-world experience. In summary, entropy is not just a scientific term, it's a unifying concept across disciplines. From explaining heat flow in physics, to quantifying uncertainty in data, to guiding decisions in machine learning, entropy helps us measure unpredictability. And by understanding it, we can better interpret the chaos, uncertainty, and surprise that surround us every day.